For more than 2 decades, the Lockheed Martin F-35 Lightning II has served as the defining symbol of American air power, a fifth-generation multi-role stealth fighter so technologically advanced that allied nations were expected to accept its terms, conditions, and costs, or simply go without. No other aircraft in modern history has combined stealth, sensor fusion, electronic warfare, and networked combat capability into a single airframe available for export. It was, by every metric the defense establishment could devise, the gold standard of contemporary fighter aviation. The origins of the F-35 lie in the Joint Strike Fighter (JSF) program, launched in the early 1990s in the aftermath of the Cold War. At that time, the United States military was confronting a peculiar strategic paradox. It had just emerged victorious from a half-century of superpower competition. Yet it operated a vast and aging fleet of dissimilar aircraft: the A-10 Warthog for close air support, the F-16 Fighting Falcon for multi-role operations, the AV-8B Harrier for expeditionary short takeoff and vertical landing missions, and the F/A-18 Hornet for carrier operations. Each aircraft required separate supply chains, separate training pipelines, separate maintenance protocols, and separate sustainment networks. The costs were staggering, and the inefficiency was systemic. The solution, as conceived by defense planners and ultimately contracted to Lockheed Martin after a competitive fly-off against Boeing in the late 1990s, was a single family of aircraft capable of satisfying the needs of all three military branches and several allied nations simultaneously. The result was the F-35 program, 3 variants sharing approximately 70 to 80% of their parts, but individually optimized for distinct operational environments. The F-35A, the conventional takeoff and landing variant, was designed for the United States Air Force and most international customers. It is the lightest of the 3, optimized for performance at altitude and equipped with an internal 25mm GAU-22/ a rotary cannon, a 4-barrel derivative of the GAU-12 equalizer, mounted in the left wing root, with a maximum speed of Mach 1.6 and a combat radius exceeding 600 nautical miles on internal fuel alone. It was conceived as a replacement for the aging F-16 fleet, inheriting that aircraft's multi-role DNA while adding a quantum leap in stealth and sensor capability. The F-35B, the short takeoff and vertical landing variant, was developed specifically for the United States Marine Corps and the United Kingdom's Royal Navy and Royal Air Force. This variant incorporates the most mechanically complex system in the entire F-35 family, a shaft-driven lift fan developed jointly by Lockheed Martin and Rolls-Royce. The lift fan, located immediately behind the cockpit, is powered by the engine's low-pressure turbine through a clutch-driven drive shaft. When the pilot transitions to vertical flight mode, the lift fan opens its doors and spins up, producing downward thrust near the aircraft's center of gravity. Simultaneously, the main engine's exhaust is redirected downward through the 3-bearing swivel module, 3BSM, a uniquely engineered nozzle system whose 3 internal bearings allow it to rotate from a horizontal to a near vertical orientation. 2 roll posts mounted under the wings discharge bypass air to provide lateral stability during slow-speed hovering. The entire system must balance 3 thrust vectors: the lift fan forward, the swivel nozzle aft, and the roll posts lateral to maintain controlled flight at 0 airspeed. It is an engineering achievement without precedent in single-engine fighter aircraft. The F-35C, the carrier-based variant, is the largest of the 3. It features a larger wing with folding wingtips to fit within aircraft carrier hangar decks, a strengthened undercarriage to absorb the shock of arrested landings, and a larger fuel fraction than its siblings. The F-35C has the greatest range of any F-35 variant, making it well-suited for the long over-water transits inherent in carrier strike group operations. It carries no internal gun but can mount an external gun pod. All 3 variants share the same Pratt & Whitney F-135 engine, the most powerful fighter engine ever placed in production. The F-135 is a derivative of the F-119 engine that powers the F-22 Raptor, but extensively redesigned with a larger fan diameter and higher bypass ratio to optimize subsonic fuel efficiency. At military power, the F-135 produces approximately 28,000 pounds of thrust. With the afterburner engaged, that figure rises to approximately 43,000 pounds, generating thrust-to-weight ratios that, despite the aircraft's considerable mass, allow competitive climb performance. The engine's exhaust nozzle features 15 partially overlapping pedals arranged in a sawtooth pattern, a design that simultaneously reduces radar cross-section from the rear aspect and creates vortices that that dissipate the exhaust plume's infrared signature. Even the afterburner incorporates radar-absorbent materials on its internal fuel injector rings and curved vanes, a degree of stealth engineering that extends deep into the propulsion system itself. The F-135 is not designed for supercruise sustained supersonic flight without afterburner, a capability that distinguishes the F-22 Raptor from all other operational fifth-generation fighters. This limitation was an intentional design trade, accepted in exchange for the greater fuel efficiency and thrust characteristics that make the F-35 viable across its diverse mission set. Critics have long pointed to this as a vulnerability in beyond visual range combat scenarios, where energy management and sustained supersonic acceleration can determine the outcome of missile engagements. The stealth architecture of the F-35 is the product of decades of accumulated American expertise in low observable design, tracing a lineage from the F-117 Nighthawk through the B-2 Spirit to the F-22 Raptor. The airframe's external geometry is carefully sculpted to deflect radar energy away from its source rather than reflecting it back. Leading edges, inlets, and control surfaces are aligned to a limited set of angles, concentrating any residual radar return into narrow azimuth spikes rather than broad reflections. The diverterless supersonic inlet (DSI), a carefully shaped bump ahead of the engine intake, eliminates the traditional inlet duct radar reflector by shaping the airflow without mechanical divergers, simultaneously hiding the engine compressor face from radar and reducing weight. The entire outer surface is coated with radar-absorbent material more durable than the coatings applied to the F-22, significantly reducing the maintenance burden that plagued earlier stealth aircraft. From certain aspects, the F-35's radar cross-section has been compared to the size of a metal golf ball, a reduction of several orders of magnitude compared to conventional fighters of its generation. The infrared signature is similarly managed. The engine exhaust sawtooth nozzle promotes rapid mixing with ambient air, cooling the plume. The aircraft's skin incorporates thermal management pathways that reduce the surface temperature differentials that infrared sensors seek to detect. Radio frequency emissions are tightly controlled. The aircraft's electronic systems are designed to operate with minimal unintentional emissions, and the pilot can selectively activate or deactivate radio transmissions to minimize detectability. The F-35 stealth is most effective against high-frequency fire control radars, the systems that guide missiles and direct anti-aircraft guns. Lower-frequency surveillance radars, operating in the VHF or UHF bands, can detect stealth aircraft more readily, but these systems suffer from poor angular resolution and cannot provide the precise targeting data needed to engage a maneuvering fighter with surface-to-air missiles. The mission systems aboard the F-35 represent its most consequential capability and the most challenging aspect of its development. At the core is the Northrop Grumman/APG-81 Active Electronically Scanned Array (AESA) radar, a system that electronically steers its beam across the sky without any moving mechanical parts. The APG-81 can simultaneously perform multiple radar functions: air-to-air surge, synthetic aperture ground mapping, and electronic warfare by rapidly switching among modes between pulses. It can track multiple airborne targets at ranges exceeding 150 kilometers while simultaneously building a high-resolution map of the ground below. Unlike mechanically scanned radars, which require physical movement and are susceptible to vibration and mechanical failure, the APG-81's electronic beam steering is nearly instantaneous and far more reliable over the aircraft's service life. The Northrop Grumman/Raytheon/AAQ-37 Distributed Aperture System (DAS) is perhaps the most operationally transformative sensor on the aircraft, comprising 6 high-resolution infrared cameras distributed around the fuselage forward, aft, left, right, upper, and lower. The DAS creates a seamless, spherical infrared picture of the environment surrounding the aircraft at all times. The processed imagery is projected directly onto the pilot's helmet visor, enabling the pilot to effectively see through the aircraft's structure in any direction. If an enemy missile is launched from below and behind, the DAS detects the launch flash and tracks the missile's approach, cueing the pilot and activating countermeasures. This gives the F-35 an unprecedented defensive awareness that no previous fighter, not even the F-22, possessed. The base systems and ASQ-239 Barracuda electronic warfare suite extends the aircraft's sensor reach into the electromagnetic spectrum. 10 antennas distributed across the airframe receive radar emissions from any direction, identify their source and type, and either alert the pilot or automatically generate countermeasures. The system can jam enemy enemy radar, disrupt communications, and gather electronic intelligence simultaneously, all while maintaining the aircraft's low observable profile. The Lockheed Martin /AAQ-40 Electro-Optical Targeting System, EOTS, mounted beneath the nose in a flush aperture that preserves the stealth profile, provides laser designation and long-range infrared tracking for precision strike missions. The Northrop Grumman /ASQ-242 Communications, Navigation, and Identification (CNI) suite handles all radio, navigation, and IFF functions through a single integrated system. The true power of all these sensors lies not in their individual capabilities but in their integration. The F-35's mission computer fuses data from all sensors into a single, coherent tactical picture presented to the pilot not as a confusing array of raw sensor returns, but as a synthesized, intuitive situational awareness display. The pilot sees the world, not a radar screen. This fusion capability, implemented through over 8.6 million lines of code in the Block 3F software configuration, was the most technically demanding element of the entire F-35 program, integrating sensors operating at different frequencies, with different update rates and different data formats, into a unified picture that a pilot can act upon in real time required software engineering of extraordinary complexity. It cost years of delays and billions of dollars in cost overruns, but the result, when it finally worked, was unlike anything previously flown. The cockpit itself reflects the philosophical shift the F-35 represents. The 20x8-inch primary touchscreen display replaces dozens of individual instruments with a fully configurable, software-defined interface that the pilot can arrange to personal preference. A smaller secondary display beneath the primary serves as a backup. Voice recognition allows hands-free command input. Most radically, the traditional head-up display projected onto a glass panel in front of the pilot has been eliminated entirely, replaced by the AAQ-37 Integrated Helmet-Mounted Display System, HMDS. The helmet projects critical flight and combat data directly onto the visor, ensuring that the pilot has access to essential information regardless of where they are looking, including during hard maneuvering turns where the traditional HUD would be out of the field of view. Each helmet costs approximately $400,000 and incorporates its own infrared cameras, auto-alignment sensors, and night vision capability. Early versions suffered from latency in the DOS imagery, a slight lag that made the see-through feature disorienting during fast maneuvers, but successive generations addressed these issues through improved processing power and software refinement. The weapons payload of the F-35 reflects its dual-mode philosophy. In its primary stealth configuration, weapons are carried internally in two side-by-side bays, each with two stations. The outer stations can accommodate weapons up to 2,500 pounds, 1,500 pounds in the F-35B, including the GBU-31 and GBU-32 Joint Direct Attack munitions, the GBU-12 Paveway 2 laser-guided bomb, and the AGM-154 Joint Standoff weapon. Inner stations carry air-to-air missiles, the AIM-120 MRAM in current configurations, with future integration of the AIM-260 Joint Advanced Tactical Missile planned. Up to 4 GBU-39 small-diameter bombs can be carried on a single outer station via a rotary launcher, providing significant precision strike capacity within the stealth envelope. As of late 2023, the F-35A achieved certification to carry the B-61-12 nuclear gravity bomb, a guided variant of the legacy B-61 that gives the aircraft a strategic nuclear strike mission alongside its conventional roles. When stealth is no longer a priority once enemy air defenses have been suppressed or destroyed, the F-35 transitions to what the Air Force calls beast mode. In this configuration, the aircraft carries weapons on 6 external hardpoints in addition to its internal bays, accommodating a total weapons load that can exceed 18,000 pounds. Wingtip pylons carry AIM-9X Sidewinders or AIM-132 SRAM short-range missiles. Inboard wing stations carry heavier air-to-surface weapons, including the AGM-158 Joint Air-to-Surface Standoff Missile and the Norwegian Joint Strike Missile, JSM. The transition to beast mode reduces stealth but dramatically increases strike capacity, transforming the same aircraft that penetrates defended airspace into a heavy attack platform that can prosecute dozens of targets per sortie. Sustaining this capability comes at a price that has become one of the program's most persistent criticisms. The F-35 costs approximately $35,000 per flight hour to operate compared to approximately $20,000 for the F-16 it was meant to replace. Across a fleet of nearly 900 aircraft operated by the United States alone, alone, and with lifetime program costs projected to exceed $1.7 trillion, the F-35 represents the most expensive weapons system ever procured. Its maintenance requirements are formidable not merely in the financial sense, but in the logistical. The program's original sustainment concept, the Autonomic Logistics Information System, ALIS, was meant to provide a global, network-based maintenance management platform that would allow any F-35 to be serviced at any facility worldwide. In practice, ALIS suffered from persistent reliability problems, cybersecurity vulnerabilities, and software instability. It is being progressively replaced by the Operational Data Integrated Network, ODIN, a cloud-based successor that has demonstrated roughly twice the diagnostic accuracy of its predecessor. The export control regime surrounding the F-35 is equally consequential. Partner nations, those who contributed funding and production work to the program, receive aircraft with hardware access but without access to the most sensitive source code governing the mission systems. Software updates require American approval. Weapons integration requires American authorization. The aircraft's most capable features are managed through a layered access system that preserves American control over the most sensitive technologies even after the aircraft has been delivered to a foreign operator. This is not a bug in the system. It is a deliberate feature designed to ensure that the United States retains leverage over Allied air forces and prevents the most sensitive American sensor fusion and electronic warfare technologies from diffusing to potential adversaries. But it creates a strategic dependency that some nations have found increasingly uncomfortable, particularly as they seek to integrate domestically developed weapons and systems. South Korea builds its own future. It was precisely this dependency that South Korea's government sought to escape when it launched the Korean Fighter Experimental (KFX) program in the early 2010s. South Korea's strategic environment is uniquely demanding. It faces North Korea across one of the most heavily fortified borders in the world, conducts ongoing surveillance and deterrence operations that impose substantial flight hour demands on its air force, and must be capable of acting independently in scenarios where American support might be delayed, constrained, or politically unavailable. Dependence on a foreign supplier for software updates, weapons integration approvals, and maintenance authorizations was not a theoretical vulnerability, it was an operational constraint with direct consequences for combat readiness. The foundational requirement for the KFX program was therefore not simply build an advanced fighter, it was build an advanced multi-role fighter that can operate, evolve, and fight without requiring permission from any foreign nation. That requirement, stated simply, eliminated every foreign fighter on the market. The F-35 was unavailable for export with full access. The Eurofighter Typhoon involved European industrial partnerships with their own export control complexities. The Boeing F-15 was capable but represented fourth-generation technology with no path to indigenous evolution. The only solution was to build from scratch. Korea Aerospace Industries, KAI, the national aerospace company that had previously produced the T-50 Golden Eagle supersonic jet trainer in partnership with Lockheed Martin, was assigned program leadership. The T-50 experience developing a Mach 1.5 capable aircraft with an American partner gave KAI a foundation in supersonic aerodynamics, fly-by-wire flight control systems, and production tooling. But a twin-engine stealth-influenced multi-role fighter was orders of magnitude more complex. Defense analysts in the United States, Europe, and South Korea itself were broadly skeptical. The barriers to entry for fifth-generation fighter development: low observable shaping, AESA radar development, sensor fusion software, advanced propulsion had previously been cleared only by the United States, Russia, and China, nations with decades of experience and virtually unlimited defense budgets. Indonesia joined the program in 2010, contributing a share of development funding in exchange for technology transfer rights and a production share. The partnership would have meaningfully reduced South Korea's financial burden while potentially providing KAI with a regional launch customer. However, Indonesia repeatedly deferred its payments as its defense budgets came under pressure, ultimately failing to fulfill its commitments. South Korea continued without interruption, absorbing the additional financial burden. The total development cost ultimately reached approximately 8.8 trillion Korean won, roughly $6.7 billion at contemporary exchange rates, borne entirely by the South Korean government and KAI. The first KF-21 prototype, designated Block 1 No. 1, rolled out of the Kai facility in Sashin in April 2021. The rollout was an event of considerable symbolic importance. The aircraft that emerged was not the somewhat boxy, utilitarian design that external observers might have expected from a nation building its first indigenous supersonic fighter. It was a sleek, purposeful aircraft whose overall geometry clearly reflected the same stealth-shaping principles that define the F-22 and F-35 canted twin tails, blended fuselage wing junction, careful edge alignment, and a forward fuselage cross-section that minimized frontal radar return. The name chosen for the aircraft, Borami, meaning young falcon or hawk in Korean, suggested not a regional interim solution but a global competitor. The first flight occurred in July 2022 when prototype number 1 lifted off from Sashin Airfield and conducted a 40-minute flight test that validated basic airworthiness and handling qualities. The flight test program has since accumulated over 2,000 sorties across 6 prototypes, systematically expanding the aircraft's performance envelope. Supersonic flight has been demonstrated. Air-to-air missile separation has been validated. The indigenous AESA radar has been tested against representative threat emitters. The results have been sufficiently impressive to accelerate the program's commercial positioning. The performance figures that have emerged from the KF-21 flight test program are striking in their content. The aircraft has demonstrated a maximum speed of Mach 1.81, substantially faster than the F-35's Mach 1.6 top speed, and comparable to legacy fighters like the F-16 Block 50 seconds. Its service ceiling exceeds 50,000 feet. Its combat radius is approximately 750 nautical miles on internal fuel, giving it a reach that covers virtually any potential target within the Korean peninsula and its surrounding waters on a single fuel load. Its maximum takeoff weight of approximately 25,600 kilograms makes it a heavier aircraft than the F-16 but significantly lighter than the F-15, placing it in a payload range sweet spot that suits the Korean Air Force's primary operational requirements. The radar system developed domestically by Hanwha Systems is an AESA array incorporating more than 1,000 transmit-receive modules. Terms: AESA radars use solid-state transmit-receive elements rather than a single mechanically controlled transmitter, enabling simultaneous multi-mode operation, extremely rapid beam steering, and low probability of intercept emissions. The ability to design and manufacture AESA radar at this level of capability is possessed by only a handful of nations, the United States, France, the United Kingdom, Russia, Israel, and Japan among them. That South Korea has independently crossed this threshold is a significant indicator of the maturation of its defense industrial base. The Electronic Warfare Suite, the Infrared Search and Track (IRST) system, the communications architecture, and the primary air-to-air missiles including the Meteor-class long-range AAM under development and the domestically developed KEPD-350K standoff cruise missile are all indigenously produced or developed. This is not merely a matter of national pride. It means that the KF-21 can be upgraded, armed, and maintained without reference to foreign export control authorities. South Korea can integrate new sensors when it develops them, field new weapons when it procures them, and update software when its engineers write it on its own timeline and subject only to its own industrial and budgetary constraints. The KF-21's approach to stealth represents a philosophically distinct choice from the F-35's all-in stealth architecture, where the F-35 carries all weapons internally to preserve a pristine low observable profile for every mission. The KF-21 employs what its designers call a semi-stealth or reduced observable approach. The aircraft features 6 semi-recessed weapon stations for primary air-to-air missiles. The weapons are partially embedded in the fuselage contours, reducing but not eliminating the radar cross-section contribution of the missiles and their pylons. 6 additional external hardpoints provide conventional payload capacity when stealth is not a mission requirement. The airframe structure has been designed from the outset to accommodate fully enclosed internal weapons bays in future production blocks, when the technology maturity and cost profile support their incorporation. This philosophy reflects a calculation that absolute stealth, the F-22/F-35 model, carries costs in weight, complexity, and operational flexibility that may not be justified for all threat environments. Against an adversary with advanced integrated air defense systems, semi-stealth aircraft face greater risk than fully low observable ones. But against most of the threat environments that South Korea, its potential export customers, and many other air forces actually face, The reduction in radar cross-section achieved by the KF-21 semi-recessed configuration may be sufficient, while the saved weight and complexity translate to higher speed, greater payload, and lower acquisition and operating costs. It is a pragmatic rather than an absolute solution. The phased development roadmap that Kai has publicly outlined reflects the ambition of the program's long-term vision. Block 1, currently completing its flight test program, is an air superiority platform with limited precision strike capability. It is scheduled to enter service with the Republic of Korea Air Force in 2026, replacing the aging McDonnell Douglas F-4 Phantom II and Northrop F-5 Tiger II aircraft that have been in Korean service since the era of the Vietnam War aircraft, whose airframes predate the personal computer, the internet, and every other technology that defines modern warfare. Block 2, planned for development beginning in the late 2020s, will introduce full air-to-ground capability, including internal weapons bays, precision strike sensors, and the integration of the full suite of Korean-developed standoff weapons. Block 2 will transform the KF-21 from a dedicated air superiority platform into a true multi-role system capable of deep strike, suppression of enemy air defenses, close air support, and anti-ship warfare. Block 3, currently in the concept development phase, will introduce collaborative combat aircraft, CCA, teaming the ability for a single KF-21 pilot to supervise and control a flight of unmanned loyal wingman drones that fly ahead of the manned aircraft, extending its sensor reach, absorbing enemy fire, and carrying additional weapons. The export market implications of the KF-21 are substantial. Poland has signed a letter of intent to acquire the aircraft. The United Arab Emirates is reportedly in advanced discussions. Indonesia, despite its payment difficulties during development, retains production and technology transfer rights. The Philippines, Malaysia, Thailand, Colombia, and numerous other nations operate air forces equipped with aging fourth-generation aircraft whose replacement is overdue and who cannot afford the F-35's approximately $80 to $110 million unit cost, depending on variant, or its $35,000 per flight hour operating costs. The KF-21's estimated unit cost of $50 to $65 million, and its operating cost profile significantly below the F-35's, positions it as an affordable high-end option for exactly this market segment. It offers advanced radar, reduced observability, and indigenous weapons integration, everything a modern air force needs without the export control strings, the political dependencies, or the sustainment costs that accompany the American aircraft. China's strategic challenge to American air power, while the KF-21 challenges the F-35's dominance through competitive capability and market disruption, a more existential challenge to American air power comes from a different direction entirely. Hypersonic weapons, defined as systems that travel at speeds exceeding Mach 5, or approximately 3,800 miles per hour, represent a fundamental challenge to the defensive systems that protect aircraft, ships, and ground installations. They are fast enough that existing missile defense systems have insufficient time to react. They are maneuverable in ways that ballistic missiles are not, rendering pre-calculated intercept solutions invalid before they can be executed. And they can fly at altitudes skimming the edge of the atmosphere at 100,000 to 150,000 feet that place them above the engagement envelopes of most existing air defense systems while below the reach of space-based interceptors. China has invested heavily in hypersonic technology for approximately 2 decades. The strategic logic is straightforward. The United States has built the world's most capable integrated air defense network around Patriot missiles, Aegis destroyers, and THAAD interceptors, all optimized against ballistic missiles that follow predictable parabolic trajectories. A weapon that can maneuver unpredictably at hypersonic speed defeats these systems not by being faster than their missiles, but by being unpredictable enough that a valid intercept solution can never be computed. The DF-17, China's primary operational hypersonic delivery system, is a medium-range ballistic missile that carries a hypersonic glide vehicle, HGV, as its payload. The missile booster lifts the glide vehicle to high altitude and extreme speed, then releases it. The glide vehicle subsequently maneuvers through the upper atmosphere at speeds of Mach 5 to 10, using aerodynamic control surfaces to alter its trajectory, dodge interceptions, and strike its target with precision. Because it spends most of its flight at lower lower altitudes than a traditional ballistic missile re-entry vehicle, and because it maneuvers rather than following a fixed arc, it defeats the predictive interception models on which Patriot and THAAD depend. Chinese scientists have made significant advances in the thermal protection systems that make this possible. Hypersonic flight generates extreme aerodynamic heating skin temperatures that can exceed 2000 degrees Celsius at Mach 10. Managing this heat while maintaining the structural integrity of the glide vehicle's nose cone, control surfaces, and guidance electronics is one of the fundamental engineering challenges of hypersonic development. Recent Chinese research has focused on steel nose cone compositions with enhanced thermal tolerance, and on novel active cooling systems that circulate coolant through critical components, protecting the guidance system from the thermal environment that would otherwise degrade its accuracy. These advances have reportedly allowed Chinese hypersonic weapons to maintain guidance accuracy at speeds and maneuver loads that previously caused guidance failures. China's 2021 test of an orbital hypersonic glide vehicle, a system that completes a partial orbit of the Earth before re-entering the atmosphere and maneuvering toward its target, caused particular alarm within the American intelligence and defense communities. General Mark Milley, then chairman of the Joint Chiefs of Staff, described it as China's Sputnik moment, a demonstration of capability that exceeded American expectations and signaled a qualitative advance rather than merely a quantitative one. An orbital hypersonic weapon can approach its target from any direction, defeating the geographic assumptions built into forward-deployed missile defense architectures. Traditional ICBM defense assumes missiles will travel over the North Pole on predictable trajectories. An orbital glide vehicle can arrive from the south, from altitudes that current sensors are not positioned to track. The United States is not without response. The Army's long-range hypersonic weapon, LRHW, nicknamed Dark Eagle, has undergone extensive testing and represents the most mature American hypersonic program. The Dark Eagle uses a common hypersonic glide body, sea hemoglobin, carried on a road-mobile launcher, providing the operational flexibility to reposition before and after launch. It is reportedly capable of speeds exceeding Mach 5 and ranges beyond 1,700 miles, sufficient to strike targets throughout a potential adversary's rear areas without exposing launch platforms to direct counterattack. The Navy's conventional Prompt Strike (CPS) program uses the same sea hemoglobin warhead integrated into the vertical launch systems of Zumwalt-class destroyers, providing a naval hypersonic strike capability that can operate forward in contested maritime environments. Lockheed Martin has received a $1.1 billion contract to integrate CPS into the Zumwalt class. The Department of Defense has allocated approximately $15 billion for Army and Air Force hypersonic weapon development between 2023 and 2027, excluding the Navy's separate budget line. The Air Force's AGM-183A Air-Launched Rapid Response Weapon, ARRW, a boost-glide hypersonic missile carried by B-52s, experienced a troubled test program but demonstrated that air-launched hypersonic strikes from standoff range are technically achievable. The Air Force is also developing the Hypersonic Attack Cruise Missile, HACM, an air-breathing scramjet-powered system that uses a different propulsion architecture than boost glide weapons, sustaining hypersonic flight with an onboard engine rather than coasting on inertia from a rocket boost. The question of whether an aircraft like the F-35 can survive a hypersonic missile threat is fundamentally different from the question of how the F-35 compares to another fighter jet. Aircraft do not duel with hypersonic weapons in the way they engage in air combat. A hypersonic missile is a one-way weapon launched from the ground, from ships, or from aircraft aimed at a specific target. An F-35 in flight, when a hypersonic weapon is launched against its base, its carrier, or its supporting infrastructure, would face no threat from the weapon itself, but the degradation of those supporting elements, airfields, fuel, weapons, maintenance, command, and control nodes, would profoundly affect the F-35's ability to continue operating. In this sense, hypersonic weapons challenge air power systems rather than individual aircraft. They are strategic weapons, not tactical ones, and their implications extend far beyond the question of how fast a fighter jet can fly. The Su-75 checkmate, Russia's contribution to the challenge of F-35 dominance, takes the form of the Sukhoi Su-75 checkmate, unveiled at the Max Air Show in July 2021 with considerable fanfare. The Checkmate is a single-engine, single-seat light tactical aircraft designed explicitly to offer fifth-generation adjacent capabilities at price points accessible to nations that cannot afford the F-35, the F-22, or Russia's own Su-57. Its target market is precisely the segment that the KF-21 also addresses: air forces in Asia, Africa, the Middle East, and Latin America that operate aging fourth-generation fleets and lack the budgets to procure Western fifth-generation aircraft. The Checkmate's design incorporates stealth-shaping principles, candid twin tails, blended fuselage contours, internal weapons bay provisions within a single-engine configuration powered by a variant of the NPO Saturn AL-41F1S engine that also powers the Su-35's. The single-engine choice reduces acquisition and operating costs, simplifies logistics, and improves the power-to-weight ratio within a given price point, but it also reduces the fault tolerance of the propulsion system. Most advanced fighters use twin engines precisely because engine failures, particularly in combat, are survivable in a twin-engine aircraft and catastrophic in a single-engine one. Russia has claimed the Checkmate will reach speeds of up to Mach 1.8, carry a significant internal weapons payload, and incorporate an advanced AESA radar similar in concept to the system on the Su-57. AI-assisted pilot decision support has been highlighted as a key feature, along with voice command interfaces and a modern glass cockpit. A carrier-capable variant has been proposed, as has an unmanned version. The projected unit cost of approximately $25 to $30 million, roughly one-third the F-35's unit price, is the central selling proposition. The Checkmate faces challenges that extend beyond marketing. Russia's defense industrial base has been severely stressed by the economic consequences of Western sanctions imposed following the February 2022 invasion of Ukraine. The war itself has consumed enormous quantities of munitions, aircraft, and material, and Russia's production capacity has struggled to keep pace with battlefield attrition of existing platforms, let alone fund and develop a new fifth-generation aircraft program. The Sukhoi Su-57, Russia's primary fifth-generation fighter, was in production at rates of only a handful of aircraft per year before the Ukraine war and has been reported operating in that conflict in very limited numbers, with apparent reluctance to expose it to the capable air defense environment. Whether the Checkmate will progress from a prototype to a production aircraft on the timelines Russia has suggested, with operational service projected for the late 2020s, is deeply uncertain. Russia's track record of announcing advanced fighter programs and delivering them substantially later than advertised is well established. The MiG 1.42/MFI program, announced in the 1990s as Russia's answer to the F-22, never entered production. The Su-57 program, initiated in the early 2000s, did not achieve initial operational capability until 2020, nearly a decade behind its original target. Potential export customers, particularly those in discussions with Russia for Su-57 purchases, including India, which ultimately withdrew from the joint development program, have learned to discount Russian program timelines considerably. Nonetheless, the Checkmate concept is strategically coherent. A capable, affordable, exportable light stealth fighter would fill a genuine gap in the global market. If Russia can deliver a functional aircraft at the claimed price point and with the claimed capability large if conditions, given the state of Russia's defense industry, it would compete directly with both the KF-21 and the lower end of the F-35 market. The fact that Russia is attempting this program, regardless of its current challenges, is itself evidence that the global fighter market is becoming more competitive at the high end. The F-35's evolution. Lockheed Martin's response to the proliferation of competitive alternatives is not to accept the F-35's eventual obsolescence but to continuously extend its capability through a sustained upgrade program. The Block 4 upgrade package, being delivered in stages through the late 2020s and into the 2030s, represents the most comprehensive evolution of the aircraft's mission system since the Block 3F software that established full operational capability. The most significant enabling change in Block 4 is Technology Refresh 3, TR3, a comprehensive replacement of the F-35's core computing hardware. The original Integrated Core Processor, ICP, and Panoramic Cockpit Display, PCD, were state-of-the-art in the early 2000s but are now approaching the limits of their computational headroom. TR3 replaces the core processing architecture with hardware that provides dramatically more processing power. Estimates suggest an order of magnitude improvement and expanded memory capacity. This is not merely a performance improvement, it is the enabling foundation for every other Block 4 capability. The new weapons, the improved radar, the enhanced electronic warfare systems, and the expanded sensor fusion all require computational resources that the original avionics architecture cannot provide. The Block 4N/APG-85 radar, developed by Northrop Grumman as a successor to the APG-81, will provide enhanced detection range, improved resolution for synthetic aperture mapping, and more sophisticated electronic warfare capabilities integrated with the main radar array. The upgraded electronic warfare suite will incorporate lessons learned from operations in contested electromagnetic environments, particularly from the experience in Ukraine and Syria, where Russian and Iranian air defense systems have demonstrated capabilities that were somewhat better than pre-conflict intelligence suggested. Lockheed Martin CEO Jim Taiclet has articulated an ambition that goes beyond incremental upgrade, the creation of what the company calls a 5th Gen Plus F-35, incorporating technologies originally developed for the Next Generation Air Dominance (NGAD) program that Boeing ultimately won with the F-47. The central proposition: 80% of 6th generation capability at 50% of 6th generation cost reflects a calculation that the marginal combat value of moving from a highly upgraded F-35 to a purpose-built 6th generation platform may not justify the cost differential for most operational scenarios. Advanced low observable coatings, potentially including the plasma-based or metamaterial approaches being explored in classified programs, could further reduce the F-35's radar cross-section without changing the airframe geometry. Enhanced autonomy features would enable the aircraft to perform certain tactical functions: threat avoidance, targeting, countermeasure deployment with reduced pilot workload or even without a pilot aboard. The concept of operating the F-35 alongside collaborative combat aircraft, CCAs, relatively affordable unmanned systems that fly ahead of or alongside the manned fighter, is central to the Air Force's operational concept for the 2030s and beyond. The Air Force has stated a goal of fielding approximately 1,000 CCAs, with 600 paired with F-35s and 400 supporting NGAD F-47s. Individual CCAs being developed by General Atomics and Anduril could provide the F-35 flight with additional sensors, electronic warfare capacity, and weapons carriage, effectively multiplying the combat power of a single human pilot by a factor of 2, 3, or more. Lockheed's Project Carrera, developed by the Skunk Works division, encompasses the Speed Racer autonomous drone, a $1 million per unit expendable or recoverable platform optimized for electronic warfare and reconnaissance in contested environments. These drones would deploy ahead of F-35 flights, characterizing the threat environment, saturating enemy radar with emissions, and providing the manned aircraft with targeting data before they enter the engagement zone. The Common Multi-Mission Truck, CMMT, a $150,000 cruise missile-class autonomous system with over 500 nautical miles of range, provides additional standoff strike capacity that allows the F-35 to deliver effects at distances beyond its own weapons range, further reducing exposure to terminal defenses. The F-22 and F-35 complementary capabilities in the American air superiority paradigm, understanding the KF-21, the checkmate, and the future of American air power requires clarity about the relationship between the F-22 Raptor and the F-35 Lightning II aircraft that are frequently compared as if they were competing designs rather than complementary platforms optimized for distinct roles. The F-22 Raptor is, by the consensus of virtually every defense analyst who has assessed it, the finest pure air superiority fighter ever built. It is powered by two Pratt & Whitney F-119 engines that collectively produce approximately 70,000 pounds of afterburning thrust, enabling sustained supersonic cruise at Mach 1.5 to 1.8 without afterburner, a capability called supercruise that allows the F-22 to accelerate rapidly to missile engagement ranges, release its weapons at high energy states, and disengage before slower adversaries can respond. Its APG-77 AESA radar is slightly less capable than the F-35's APG-81 in terms of ground mapping and electronic warfare, but is optimized for the long-range air-to-air detection mission, achieving detection ranges against typical fighter-sized targets that classified briefings suggest significantly exceed 200 kilometers. Its thrust vectoring nozzles allow the F-22 to perform post-stall maneuvers at angles of attack that no conventional fighter can match. including the famous Cobra maneuver that bleeds speed to achieve a firing position on an overshooting adversary. Its radar cross-section is smaller than the F-35's and is maintained with extraordinary care. The F-22's stealth coating, applied in a classified process, requires more intensive maintenance than the F-35's more robust coating but achieves lower radar observability across a broader range of threat frequencies. The F-35's strengths lie elsewhere. Retired Marine Corps pilot and first operational F-35B Squadron Commander David Burke has described the F-35 as functioning like a quarterback, not the fastest or most agile player on the field, but the one who sees the entire game, processes the information, and tells everyone else where to go and what to do. The F-35's sensor fusion architecture, its data links, and its ability to share its synthesized tactical picture with other aircraft, ships, and ground stations in real time give it a force multiplier effect that extends well beyond its individual combat performance. An F-35 that detects a threat with its AESA radar while maintaining radio silence can share that detection with F-22's that can engage from beyond the threat's detection range. The combined effect of the two aircraft, the F-35's sensor and the F-22's shooter, is greater than either could achieve independently. The F-22's limitation is exclusivity, with only 187 operational aircraft in the U.S. Air Force inventory, a fraction of the 750 that were originally planned before budget pressure forced program termination in 2009. The Raptor is a scarce resource that cannot be present in all the theaters where it might be needed simultaneously. The F-35, with over 900 aircraft now delivered across the U.S. and Allied Air Forces and production continuing at approximately 150 aircraft per year, provides a numerically significant fifth-generation presence across all theaters. The combination F-22 for the hardest high-end air superiority fights, F-35 for everything else defines the American fifth-generation posture. The fracturing of the American monopoly. The convergence of developments described in this article represents something genuinely new in the history of military aviation. The end of the American monopoly on fifth-generation fighter technology. For the first 2 decades of the 21st century, the United States was the only country with operational fifth-generation fighters. The F-22 achieved initial operational capability in 2005, the F-35A in 2016. Russia's Su-57 did not reach initial operational capability until 2020, and then only in small numbers. China's J-20 entered service in 2017, but with an imported Russian engine rather than the domestic WS-15 that Chinese engineers were still developing, limiting its full capability potential. No other nation had crossed the threshold. The KF-21 Borami changes this. South Korea, a nation with no prior experience building supersonic combat aircraft before the T-50 trainer in the early 2000s, has designed, built, and flown a competitive fifth-generation adjacent fighter that will enter service in 2026. Its radar, electronic warfare suite, and weapons are indigenous. Its export control restrictions are those of South Korea alone. Its operating costs are substantially below the F-35's. And its development trajectory: Block 1 air superiority, Block 2 multi-role, Block 3 autonomous teaming mirrors the ambitions of sixth-generation programs at a fraction of the cost. This matters not because the KF-21 is superior to the F-35 in every dimension. It is not. The F-35's sensor fusion architecture, its software sophistication, its stealth maturity, and its integrated logistics network represent accumulated American investment that cannot be replicated overnight. But it matters because it demonstrates that the barriers to entry for advanced fighter development are lower than American defense planners assumed. If South Korea can do it, Japan can do it and is, with the Mitsubishi FX program. If South Korea can do it, Turkey can attempt it and is, with the Taikon. If South Korea and Japan and Turkey can do it, the export market for American fighters faces structural competitive pressure that no amount of incremental F-35 improvement can entirely eliminate. The hypersonic dimension adds a different kind of pressure. American air power depends on the ability to sustain operations from forward bases, airfields, carriers, logistics nodes that are increasingly within range of precision Chinese and Russian hypersonic weapons. An F-35 is useless if the base it operates from has been cratered, its fuel storage destroyed, its maintenance personnel forced into shelters, and its command and control infrastructure disrupted. Hypersonic weapons do not make fighters obsolete. They change the strategic calculation about where fighters can be based, how many can be sustained in theater, and how quickly they can be made combat-ready after an initial strike. The American response: distributed basing, hardened infrastructure, defensive hypersonic interception systems, and offensive hypersonic weapons of its own is underway but not yet mature. The F-35 will remain the backbone of American and Allied air power for at least the next 2 decades. Its sensor fusion, its stealth, its production scale, and its continuous upgrade program ensure that it will remain relevant long after its initial critics expected it to be replaced. The F-47, when it enters service, will address the high-end air superiority role currently handled by the declining F-22 fleet with 6th-generation capabilities: directed energy weapons integration, advanced low-observable coatings, potentially unmanned or optionally manned operation, and propulsion systems that enable sustained operation at the edge of the atmosphere. But the world in which the F-35 was conceived, a world where only one nation could build advanced fighters, where Allied nations had no choice but to accept American terms, and where stealth was a sufficient guarantee of air superiority, is no longer the world that exists. South Korea just built the alternative, and that changes everything about how the next chapter of air power will be written.